There's been a lot of talk about orbital data centers recently. Instead of collecting solar energy in space to send back to Earth, the idea is to move the energy-consuming computer server data centers off the planet into orbit, and just move data around, something we know how to do. It's an interesting idea, but what is not clear is whether it is actually a practical idea. We're going to go through what it will take to build a data center in low Earth orbit, like the one that Axiom is proposing here. What's your prediction? Practical or not practical? I'm going to make a lot of assumptions along the way. Feel free to choose your own numbers if you think that I'm off target. Let's start at the small end, and I'm going to arbitrarily pick 250 servers as the target. In a terrestrial data center, that would take up about 6 racks of space, and many companies have their own data centers of this size. The big companies have much larger data centers. These are the Microsoft data centers in Quincy, Washington. You'll need to squint to pick out the cars in the parking lots. We'll need some space for our servers. I don't know exactly how much space to allocate, so I'm just going to ask the European Thales Alenia folks to build us a module like the Lunar Gateway Halo module. That gives us 125 cubic meters, or 4,400 cubic feet of space to use. That may seem like a lot of space for 250 servers, but we do need space for power distribution, cooling, control systems, and communication electronics. We also need systems for station keeping and alignment to keep us in the right location and pointed in the right direction. We also need to power our servers. I'm going to pick 500 watts of power use per server, and that puts the overall power requirements at 125 kilowatts. There will be inefficiency in power conversion, there will be other systems using power including ground communication, and the solar panels will degrade over time. And it's good practice to have some headroom in any design. I'm going to double the power requirements up to 250 kilowatts, and that will be our solar power target. We will need panels that can easily be produced in high volume and are reasonably cheap. And an easy choice is the panels used on the Starlink Block 2 Mini that is currently being launched by Falcon 9. Each panel is 12.8 meters by 4.1 meters and has a surface area of 53 square meters. With quality solar cells, each square meter will produce about 240 watts, or 12.7 kilowatts for each array. We need 20 panels to generate the 250 kilowatts that we need. Here's what that looks like. Our little module is surrounded by a swarm of solar arrays. Looks a bit silly, but servers are very power hungry. There's a significant issue that we need to deal with. If our data center is in a 400-kilometer orbit, it has an orbital period of 80 minutes, and 39% of the time is spent in darkness. During that time, our solar panels produce no electricity, and that will be 31 minutes every orbit. We therefore need battery backup systems to provide 250 kilowatts of power for 31 minutes, which is roughly what these commercial systems can do. They're fairly bulky, and they weigh about 11 tons. This is our 250 kilowatt array, which provides us the power to run our data center, but doesn't provide enough power to charge the batteries to keep it running during the night. Let me introduce our 40-panel array that can generate 500 kilowatts of power. The large number of panels plus the battery backup is unfortunate. Is there a way we could optimize that? Higher orbits are wider orbits, and that means less time in the Earth's shadow. If we go from 400 kilometers up to 2,000 kilometers, we go from spending 37% of our time in shadow to 27% of our time in shadow. That seems like a good thing. Unfortunately, if we push out to 2,000 kilometers, our time in shadow goes up to 245 minutes. The percentage of time has gone down, but the higher orbit has an orbital speed that is 10 times less, and that is what pushes the time in shadow up so significantly. If we want to keep the data center going during the shadow period, we need a battery that is 8 times larger. We can reduce the panel count by 20% because we have more time to charge in the solar orbit. Not really an obvious win. We could skip the batteries and go with an architecture without batteries and just shut down the data center during the shadow times. If you do this, you need to shift workload to other data centers during the shadow time. You need a constellation to provide 24/7 service. The lag at 2,000 kilometers is 5 times the lag at 400 kilometers, though it's only 13 milliseconds at 2,000 kilometers. The lag is variable depending on where you are in the orbit. And it costs more to launch to the higher orbit. On the plus side, your orbital lifetime is longer, and you need fewer satellites in a constellation. And since you aren't using batteries, your solar array is half the size. We also need to provide temperature control, and we all know
it is very cold in space.
Khan may have been a genetically engineered superhuman, but that apparently left little time to study thermodynamics. Spacecraft are surrounded by what we call a vacuum. You are probably familiar with thermos bottles, which keep hot fluids hot and cold fluids cold by using a vacuum to separate the liquid from the outside environment. With the exception of the stopper to close the top of the bottle, the only way for heat to move between the inside and outside is by radiation across the vacuum. With our data center, you've closed off the stopper end of the thermos, used a better vacuum, and you stuffed a 250 kilowatt space heater inside. Does that mean it will get too hot? Yes, and we can figure out how hot that will be. We know how much power is going into it, we know how much surface area the module has, and we know how good the aluminum is at emitting heat. We also remember the equations required to calculate the temperature. We're hoping to keep our servers at about 72 degrees Fahrenheit, or 295 Kelvin. When we do the math, we find that the temp of our module is going to keep going up until it hits 1067 Kelvin. Unfortunately, the aluminum in the module melts at 933 Kelvin, so I think we have a bit of a problem. That is, however, assuming polished aluminum, which is very bad at radiating heat away. If we pick a coating that is much better, the estimated temperature drops to 490 Kelvin, a mere 880 degrees Fahrenheit, or 217 degrees Celsius. This estimate ignores the heat that we'll pick up from the sum, which is made worse by the coating that makes the module better at radiating heat away. We need more surface area to get rid of our heat. This is a common problem for spacecraft. It's hard to get rid of heat. If we look at the ISS, it has 2 large radiator arrays to get rid of the heat from the station, and it has small radiators to keep the power conversion electronics for each solar panel array cool. Inside the space station, they use water to remove extra heat. Water is good because it can hold a lot of heat and is not hazardous if it spills. It's not great at radiators because it can freeze in the space environment, and there is therefore a heat exchanger to transfer the heat to ammonia that is pumped through the radiators. These are the radiators used on ISS. Each wing of radiators is 3 meters by 13.6 meters, or 43 square meters, and can dissipate 11.6 kilowatts. We need 250 kilowatts of dissipation, and that means 22 panels. Here are the 22 radiator arrays that we need. Our completed spacecraft is roughly the size of the completed ISS. Can we reduce the radiator area? What we need is a smaller amount of hotter coolant, as that will work better in the radiators. To convert a lot of moderately warm coolant into a smaller amount of hotter coolant for the radiator requires a heat pump. This isn't a new idea. There have been a number of papers that looked at this, and they have nicely done the hard work for us. There is no free lunch. To move the heat around requires compressors, and those require power, and that's more power for your solar panels to provide and more heat to dissipate. The conclusion in one paper was that a heat pump that gives you a 60 Kelvin increase in temperature would give you a decrease in radiator area of 30%. Not quite the 50% we were hoping for, but that would take the design from 22 radiators down to 16. You will be trading off fewer radiators, which gives you reduced manufacturing and launch cost, against a heavier cooling system, probably more solar panels, and more complexity and decreased reliability in the cooling system. I'm not really excited about this. There's also another issue. This chart shows the altitude of the ISS for a 12-month period from April 2017 to April 2018. During that time, the orbital altitude of the ISS had to be increased 9 times. Our spacecraft is the same size, but it has more drag, so we can expect it's going to need ongoing reboost if it is in a 400-kilometer orbit. How much is this beast going to weigh? Time for a poor estimate. It's very hard to find numbers for deployable solar panels, but 10 kilograms per square meter is a reasonable ballpark estimate. That gives us a mass of about 10.6 tons for the solar panels. The batteries are about 11 tons in commercially available systems. We can probably get lighter than that with a custom design. The ISS radiators are 1,123 kilograms per section, and we need 22, so that's 24.7 tons. I'm going to benchmark the servers themselves at 5 kilograms each, and with 250, we get 1.3 tons. And I'm going to allocate another 9 tons for the module and everything else we need in it. That gives us a total of 57 tons, and I'm sure there are parts that I forgot to include. We need a rocket to launch this. A fully expended Falcon Heavy springs to mind, as it can do 64 tons to low Earth orbit. Except that it can't, because the second stage and payload adapter are pulled directly from the Falcon 9 and they top out at about 19 tons of payload. You could probably pay SpaceX to modify the third stage, but it would not be cheap, and you would also likely need a very big custom fairing, also not cheap. SLS has plenty of oomph to do it, but you might need to do upper stage modifications and a new fairing, and it's a hard rocket to schedule, and an even harder one to pay for. Which leads us inevitably to Starship, which would be a nice launcher for our orbital data center. There is an alternative that might work a little better. Let's take a solar panel that is 2 meters by 2 meters, and that gives us 4 square meters. If we put in some high-efficiency solar cells that generate 300 watts per square meter, that gives us 1200 watts per power. That's probably enough to run a single 500-watt server and have enough spare power to charge batteries for the nighttime and run the other systems. We mount the server to the back of the solar cell. Attached to the back of the server is a radiator that can dissipate 270 watts per square meter, or 1080 watts total. That should be enough to dissipate the 500 watts from the server, and also deal with the heat gained by the solar cells. We can probably get away without a big cooling system, and we don't need electronics that can handle large amounts of power. You could just build a lot of these, attach them to a small spacecraft that can handle station keeping and orientation, and go from there. This does give us an interesting benchmark for orbital data centers. We're inherently limited by the area it takes to generate power to run servers and radiate away excess heat, and the minimum area is on the order of 4 square meters per server. And that's the story on orbital data centers, at least the way I see them. Practical or not practical? How do you vote? The orbital data center is going to be very big and very complicated. You will spend a lot of time and money on design of the solar arrays, radiators, cooling systems, power systems, and the rest of the spacecraft. Then you have to pay for launch costs, operational costs on the ground to monitor it, and if it's in low Earth orbit, it's going to have a short lifetime, or you're going to have to pay to refuel it. The only big benefit I see is that you aren't paying for the electricity that you use, but that's less than $100,000 a year for our 250 servers if you're paying commercial power rates. If you enjoyed this video, here's your song of the day.